BeamNG.Drive is an insanely powerful racing game because of its innovative physics engine. BeamNG is one of few racing games that properly simulates vehicle damage. And because of that, it can be a great platform for all sorts of scientific investigation and experiments. As my culminating assignment for my physics class, in this video I'm going to analyze the effect of gravity on the projectile motion of a car jumping off of a ramp in an effort to see just how much a change in the strength of gravity could impact our daily lives and Earth technology. Let's get started. Now, like any high school physics class, we log everything we do to make sure that the experiment is repeatable. Let's start with the purpose. This demo is designed to show the effect of gravity on a car jumping off of a ramp. We will demonstrate this by using one of BeamNG's coolest features, the ability to change the strength of gravity. BeamNG lets you have as low as negative Earth gravity, meaning things will fall upwards, and as high as the gravitational strength of our sun. Playing with this slider will pretty much smash everything in your simulation and probably create this: a triangle of transcendence. Note that BeamNG is still full of bugs. We're going to be testing with Earth gravity, Mars gravity, and Jupiter gravity. Now, in a normal experiment of this caliber, the materials requirement would be pretty hefty. We'd somehow need to get 27 different cars to 3 different planets, somehow create the exact same scenario on each planet, and have some way to record all of the data. BeamNG.Drive makes this process much easier. I started with the default grid map, an environment full of obstacles, jumps, and other objects. I chose to use these ramps and then deleted everything behind them with the world editor. I used this car and gave each one a different color for each trial. There's going to be 3 trials for each gravity and jump height, meaning I'm ruining 27 virtual cars. I then set up camera paths and replays so that you guys could watch the carnage up nice and close, and so that I could watch it from far away so that I can gather the data I need. The procedure of this experiment is in 2 major parts. Firstly, the actual crashing. For each trial, I made sure that the cars were at the exact same starting point relative to the ramp. However, I had to move them individually because placing cars inside each other kinda breaks the game. I then started recording with BeamNG's replay system, which will let me replay the simulation at any position and speed later. I then put the pedal to the metal and only released the gas once the vehicles reached the top of their respective ramps. I watched them fly, then repeated for each trial. I'll show you some of my favorite highlights. The next step of the procedure is to use the replays to record the simulations from a top and side angle. This will allow me to use the grid part of the grid map to measure the car's total displacement or the distance it travels. Unfortunately, BeamNG does not have a measuring tool that I know of, so we're going to be using the grid of the grid map, which is apparently 1 square meter. The exact units don't matter anyway once we have our projectile curves, which were calculated manually in Photoshop and then imported into Excel. And this is what our data looks like. After numerous hours of manually graphing and transcribing the data, this is what we get. Let's first start by just explaining our Excel spreadsheet. There are 4 major sections: the trial number of each experiment, and the average between the 3 trials. We then have 3 data points per trial: the start point, the highest point the car reached, and the point of landing, which is the farthest point the car reached. We then have an X and Y value for each point of data. We have 3 starting heights to represent the 3 ramps in the map: a 1 meter jump, a 2 meter jump, and a 4 meter jump. and of course, the 3 planets that we are conducting the experiment on. So, 3 trials plus 1 for the average, 3 points of data for each trial, 3 starting heights, 3 planets, and 2 axes for each point of data. That's 216 individual points of data. There are a lot of differences between each of these graphs, so let's take a closer look. Firstly, we can see that the lower the gravity is, the higher each and every car flies. This makes sense, as there is less force pulling each of the vehicles down. The highest point a car reaches on Mars' gravity, which has a strength of about 3.7 meters per second squared, is 28 meters. Whereas the highest point a car reaches with Jupiter's gigantic pull of gravity, 24.8 meters per second squared, is only 8 meters. Another thing I notice is that the cars actually travel horizontally farther with the lower gravitational forces. I believe this is due to how I handled the car's initial run to the ramp. While every car had the same distance to run to reach their ramp, instead of ensuring that the cars jumped at a specific speed, I simply held the gas down. While it may have been a more controlled experiment to have kept a close eye on the gas, I was worried that constantly monitoring the vehicle's speed might have brought some other unwanted forces like extra friction from braking or potentially slipping tires. Regardless, since every car had the same amount of time pushing as hard as they can to go as fast as they can, what this data shows is that some force related to gravity was actually slowing these cars down. I noticed that the car's physical structure was affected by the strong gravity from Jupiter, and I've definitely played enough with this game to know that almost any car put under the sun's gravitational force will practically turn into tinfoil. This is moon gravity, this is Neptune gravity, and that is Jupiter gravity. And if you go sun gravity, all the windows break. I saw in one of the tests that the car's bumper actually came off while it was running up, and I think what happened is the cars were suffering from an insane frictional force. On Earth, a car's shock absorbers have to overcome the force of gravity, and when traveling, a tire will use the force of friction to its advantage. The force of friction can be calculated by multiplying a calculated coefficient value by the mass of the object, which is measured in kilograms or pounds for you Americans, and the force of gravity. On Mars, a car's tires have less traction with the ground, but the car's engine will exert the same amount of force, and the strength of the gravity may have been high enough to prevent the car's tires from spinning out, meaning it is easier for the car to push faster. On Jupiter, it would then be harder for the car to push faster, plus it might have had to deal with an extra force of friction. The car's suspension clearly doesn't have enough strength to hold the vehicle entirely up as high as it's supposed to on Jupiter, as visualized here. Being a sports car, this vehicle is already engineered to have a low ride, and with this compression in the shock absorbers, it's very likely this car was dragging parts of itself along the track, creating a whole load of extra friction, and probably causing the weakly attached bumper to fall off on jump. So, by just looking at the title, you'll probably be thinking that I've already analyzed the data already, but I'd like to clarify a few things and just explain the phenomenon of gravity a bit further. Gravity is the force of a celestial body, meaning a large body in space, not the game, on the objects close to it. Without gravity, if you threw a ball, it would just keep flying upwards. If you jumped, you would never fall down. If you drove a car off of a ramp, it would never come back. Gravity is the force that powers the proverb, "What comes up must come down," and it affects every single thing on the planet. If you've ever watched Bill Nye the Science Guy, you know that everything falls at the same speed, and 2 objects at the same height will land at the same time despite their mass.
You want to see it again on the instant replay close-up camera of science? See, they hit the ground at the same time.
Bill Nye the Science Guy.
If you were able to adjust the strength of gravity, or if you were able to go to a physically smaller or larger planet with weaker or stronger gravity, then you'd find that both of those 2 objects would land at a different time than on Earth, but still the same time relative to each other. And although we can't go to Mars or Jupiter yet, we can play Earth-made video games like BeamNG.Drive and collect data from those games. My data and the shape of the charts show that the strength of gravity affects everything on the planet in the exact same way. You can clearly see how the 4-meter high jumps get to consistently about 3 times higher than their 2-meter jump counterparts, regardless of what planet or gravity level the jumps are occurring on. The basic idea here is that gravity pulls everything in the same direction at the same rate. If you want to get technical, this rate is called acceleration. The speed the vehicles are falling is increasing, but the rate at which the speed or velocity is increasing is the same. Acceleration is measured in meters per second, or meters per second squared. I've been into BeamNG.Drive for a little while now. One of my friends persuaded me to buy it, and although it feels like an expensive game for what is pre-built into it, that's not the point of the game. The point of BeamNG.Drive is for you to mess around and play with things, and that's what's led me to the idea behind this experiment. When I was given a period by my physics teacher to think of an idea for my course culminating, I knew I had to do something in BeamNG, and what are my favorite things to do in the game? Break things and screw with the gravity slider. There's a lot of experiments I could have come up with involving this game, but I thought it would be so cool to prove an existing physics concept by comparing it to how it would function on other planets. I mean, watching a car fall from a height so unnaturally fast with sun gravity is definitely a different experience. Watching that from the point of view of inside the car, it's even crazier. As many culminating activities in the Ontario high school curriculum like to do, I was assigned to research a career relating to this demonstration. I already knew off the hop that I could definitely use this knowledge to ascertain how a vehicle would operate on a different planet to design something like a Mars or Jupiter rover. In an effort to find a specific job title, I hopped on our school and board recommended life planning software, My Blueprint. Although I found many career paths that might lead to designing a Jupiter rover or a MALP for Stargate Command,
MALP en route, receiving MALP telemetry.
What's it doing?
Flying, sir.
Malps can't fly.
Apparently they can.
Shouldn't there be a memo on this stuff?
I do not believe we are still in control.
Run a systems diagnostic on the MALP.
Unfortunately, it seems like the most likely path, at least on the options on my blueprint, is also the most vague. Automotive engineer. Someone who designs and oversees the manufacturing of many products. Wouldn't a company's CEO or plant manager at Foxconn do kind of the same thing? It's kind of a vague description. Anyway, I found a different, specific job on Indeed that GM was looking for. Control system engineering. While this job relates to vehicles on Earth, I could see how a vehicle would need to have its control systems completely reworked to accommodate for the different surfaces and gravity strengths of another world. Higher-end modern-day cars are well optimized for the various services and environments here on Earth, and typically let you change between them with some sort of setting or slider. These settings can adjust things like ride height, how traction control or stability control will operate, and where the vehicle focuses on delivering its power to. In the years ahead, as space agencies like NASA and SpaceX work towards getting people to live on Mars, we're going to need innovative new vehicles. As seen with this experiment, those vehicles are going to need innovative new traction control systems. As with the power a number of vehicles have, it is very easy to lose control, even on Earth, let alone with the lighter gravitational force that exists on Mars. For this career listing on Indeed, General Motors is looking for someone who has an experience in automotive control system design, including safety standards, knowledge, and communication protocols. They're looking for someone who, at minimum, has a bachelor's degree in computer science, mechatronics, electrical, computer, or software engineering. The listing describes someone with experience in software design, embedded C or C++ programming, and Simulink modeling. Hey, I've worked with C++ on some microcontrollers. They are clearly looking for someone who's experienced in the field of autonomous driving and safety systems, most likely so that they can expand their company's portfolio in the self-driving space and improve upon their existing technology. Thanks for watching. This was a fun little project to complete, and I hope you learned something about how gravity works, because I sure did. If you want to see more interesting projects like this, make sure to subscribe. I've got an upcoming project in the works involving some of that embedded C++ programming I just talked about. Everything past the end of the resistor, all this is solder. You should also check out the Discord. It's a cool place, and they say it gets colder. You're bundled up now, wait till you get older.
But the media man beg to differ, judging by the hole in the sun.